For this activity, we are going to require some graph papers, a pencil, a ruler, maybe some rough sheets, and a pen. That's it. We take a rough sheet and take a system of equations. We call the first system of equations as system A. When we talk about system of equations, we make use of more than one equation. Let us start with the first one. Say 2x minus y plus 1 equals to 0. This equation is a linear equation as the degree of x and y both is 1. When we plot the graph of this equation, we get a straight line. We are trying to plot the graph of this particular equation. For that, this equation can be simplified and written as y is equal to 2x plus 1. Therefore, I can write y equals to 2x plus 1. Substituting values for the variable x on the right hand side, we can obtain corresponding values for y. Let us check this. We start with the values of x. Suppose x is equal to 0. You can assume any number of your choice, provided the numbers which you obtain after calculation also lie on the graph. That is the only condition. We get y is equal to 1 because 2 into 0 is 0 plus 1 gives you 1. So if I have to mark the coordinates, I would get x comma y equals to 0 comma 1. To plot a line, we require minimum 2 points, and to be sure whether our calculations are right or wrong, we take help of 3 points. So let us try and find 3 different values of x and y. We took the first value to be 0. Let us assume any number other than this, say maybe 1. If I substitute x is equal to 1, I'll get 2 into 1, that is 2 plus 1 gives me a 3 here. So my next point on the line would be 1, 3. Let us assume another value for x, say maybe 2. When I substitute 2 in place of x, I'll get 2 into 2, that is 4, plus 1 gives me a 5. This gives you 2, 5. So now we have obtained 3 points which lie on the line 2x raised to 1 minus y raised to 1 plus 1 equals to 0. As we were talking about a system of equations, definitely we require one more set of equation or one more linear equation here. The second linear equation which we are going to consider, let us begin with the second equation. X minus 2y plus 8 equals to 0. Therefore, we can write x is equal to 2y becomes positive when it goes on the other side, and plus 8 becomes minus 8. Now this is our required equation. Over here we have y on the right hand side. Therefore, we would be assuming values for y. Let us start with the first set of values. You can assume any value for y. I have taken the value for y, first value for y, to be 0. Suppose y is equal to 0. I would get x is equal to minus 8, which can be a bit difficult on the graph paper. So therefore, we try to take values which will allow us to plot the points very easily on the graph paper. Let us take a bit more bigger values. Let us start with y is equal to 4. If I take y is equal to 4, we get 2 into 4, that is 8 minus 8 giving us 0. The next value of y is say maybe 3. We get 2 into 3 is 6 minus 8 giving us minus 2. Let us put the next value for y as 2. When I substitute 2 into 2, minus 8 gives us minus 4. So we got 3 points on the line x minus 2y plus 8 equals to 0, namely 0, 4, minus 2, 3 and minus 4, 2. Now if you observe, all these 3 points are very easily plottable on the graph paper. That is why we have taken these, and we did not make use of y is equal to 0 because it would have given us minus 8, 0, which is towards the extreme end of the x-axis. So we are trying to avoid that value. Now let us try and plot this graph. To plot the graph, we will first take the graph paper. We will try and draw the x and the y axis on the graph paper. Now the x and the y axis, we can start plotting the numbers, starting with 0 at the point of intersection. Let us name the axis. The positive side of the x-axis is named as x. The negative side is named as x dash. The positive side of the y-axis is named as y. The negative side is named as y dash. Also, we are going to plot this particular lines, or we are going to number them with the help of certain scale in our mind. The scale generally used would be 1 centimeter equals to 1 unit on both the x and the y axis. So we mention directly as on both axes. So we take 1 centimeter, that is the one complete box on the graph, as 1 unit of the graph. Continuing in the same manner, I can plot points 1, 2, 3, 4, 5, 6, 7, 8 and so on the positive side. Similarly, I can plot -1, -2, -3, -4, -5 on the negative side. I can have numbers like -1, -2, -3, -4, -5 on the negative y-axis, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on the positive y-axis. Now our coordinate system is ready. The only thing which is required is to plot the graph correctly. Just to recall, this was the first equation which was with us. The first point that we got on the equation was 0, 1. We look for 0 on the x-axis and 1 on the y-axis. We look for 0 on the x-axis and 1 on the y-axis. Let us search for 0 on the x-axis and 1 on the y-axis. This is our first required point. We call it as 0, 1. The next point that we need to plot is 1, 3. The first coordinate again goes to the x-axis, the second on the y-axis. So we would be searching for 1 on the x-axis and correspondingly we move towards 3 on the y-axis. This is where we obtain the point 1, 3. The next point is 2, 5. Let us search for 2 on the x-axis and we go in the straight line following it till 5 on the y-axis. We obtain the point 2, 5. Let us draw a straight line which passes through all 3 of these points. Now this is a line of the equation 2x minus y plus 1 equals to 0. So we write the equation on the line. Following the same procedure for the second line which we had obtained in set of equations 1, we can draw a graph on the same graph paper which would look somewhat like this. This was the first line we had taken, 2x minus y plus 1 equal to 0. The second line we had taken was x minus 2y plus 3 equal to 0. All the points on the graph are already plotted. Now if we observe, what do we see here? These two lines intersect at one single point, meaning this point lies on both the lines, or this point is also known as the common solution for both the lines. It is known as the common solution. Also, we have only one common point, therefore it is known as a unique common solution. Now why does this happen, or what do you think could be the reason? Should we always check a system of equations by plotting the points? Or is there any other shorter method without plotting the points which tells us whether the equation will have a unique common point? Let us check that. For that, let us look at the equations again. We had set A of equations, that was 2x minus y plus 1 equals to 0 and x minus 2y plus 8 equals to 0. Now if I want to check whether this set of equations will have a unique solution or not, the first thing which I need to do is we need to bring the equation in the standard form of ax plus by plus c equals to 0. That is, the first term should be the x term, then the y term, then the constant equals to 0. As we have two equations with two different coefficient sets, the first equation can be called as a1x, b1y and c1. The second can be called as a2x plus b2y plus c2 equals to 0. Comparing the coefficients, we obtain a1, that is the coefficient of x in the first equation, equals to 2, b1, that is the coefficient of y in the first equation, equals minus 1, and c1, the coefficient or the constant term, is equal to 1. Let us look at the second equation. The second equation, the term or the coefficient with x is known as 1, b2, that is the coefficient is y, is minus 2, and c2, the constant, is equal to 8. Let us look at the ratios of these values which we have obtained. If I check a1 upon a2, I would obtain 2 upon 1. Whereas if I check b1 upon b2, I obtain minus 1 upon minus 2. If the minus signs get cancelled, this is equal to 1 upon 2. On observing, I find that a1 upon a2 is not equal to b1 upon b2. This is exactly what we get if I take any set of equations which give me unique solutions. So here we have learned that any set of equations which give you unique solution can be obtained if the coefficient of x of the first equation divided by coefficient of x of the second equation is not equal to coefficient of y of the first equation divided by coefficient of y of the second equation. Now, is this what always happens? Do always lines only intersect each other? Or is there anything else that can also happen? Let us see by taking another set of equations. Let us take another set of equations. Let us call this set of equations as B. Let us take equation x minus 2y minus 5 equals to 0. If I reduce this, this again gives me x is equal to 2y plus 5. Here again the coefficient on the right hand side or the variable on the right hand side is y. We will substitute values or numbers in place of y to obtain corresponding values for x. So let us make a table of these values. We have x, y, x comma y. If suppose I substitute 0 in place of y, I would get 2 into 0, that is 0 plus 5, again giving me 5. Substituting minus 1 in the same manner, we obtain 3. Minus 2, we obtain 1. This gives us sets of 3 points, that is 5, 0, 3, minus 1 and 1, minus 2. Using these 3 points, we can plot the line x minus 2y minus 5 equal to 0 on the graph paper. Let us take another equation here. 3x minus 6y minus 15 equals to 0. If I divide the entire equation by 3, what do I get? I get x minus 2y minus 5 equal to 0, which is nothing but the previous equation precisely. Again, if I want to find points on this equation, the points will be the same. I can have many more points as a line has infinitely many points. So now let us try and plot the graph of these two lines, that is x minus 2y minus 5 equals to 0 and 3x minus 6y minus 515 equals to 0. Following the same procedure, the graph which we obtain would be this. Now if you look at this graph, we have the first point, which is 5, 0 is here, x-axis 5, y-axis 0. The point 3, minus 1, 3 on the x-axis, minus 1 on the y-axis. And the last point is 1, minus 2, 1 on the x-axis and minus 2 on the y-axis. We have drawn a straight line passing through the 3 points. Now, if you can observe, both the equations are written on the same line, meaning both these lines represent, or both these equations represent the same line. How many common points do both these equations have? All the points on this line are common solutions to these equations, meaning there are infinitely many solutions possible for these equations. Now, when does this happen? Algebraically, let us check that, or let us check that if the coefficients of the equation are able to help us find if a given set of equations will have infinitely many solutions or not, as in the previous case. We had our equation x minus 2y minus 5 equal to 0. Here again comparing with a1x plus b1y plus c1 equals to 0, we obtain a1 is 1, b1 is minus 2 and c1 is minus 5. Same way we had the next equation was 3x minus 6y minus 15 equal to 0. We obtain a2 is equal to 3, b2 is equal to minus 6 and c2 is equal to minus 15. Let us check the ratios as we did in the previous case. We'll get a1 upon a2 is 1 upon 3, b1 upon b2 is equal to minus 2 upon minus 6, which surprisingly turns out to be 1 upon 3 again. Let us check for c1 upon c2 is again equal to minus 5 upon minus 15, which is equal to 1 upon 3. What do we learn from all these three ratios? We see that a line can have infinitely many solutions if and only if a1 upon a2 is equal to b1 upon b2 is equal to c1 upon c2. Is this what only happens, or are there any system of equations which do not have any solution at all? Let us again check that. Let us take the third set of equations and observe what happens here. Let us take set C of equations. We take the first equation as 2x plus 3y minus 6 equals to 0. If I reduce this equation, I would obtain x is equal to 6 minus 3y divide by 2. I am dividing 2 for each term. This gives us 3 minus 3y upon 2. As we observe, there is a denominator 2. We would try to eliminate it by taking even values for y. You can also take odd values, but then that gives you decimal values for x, which are a bit difficult to plot on the graph paper. So to avoid complications, we are trying to take even values for y. Let us begin with 3 sets of values as we did before. We start with, say, y equals to 2, which is an even number. If I substitute 2 here, 2 gets cancelled with the denominator 2. I would get 3 minus 3, which gives me a 0. If suppose I put a 0 here in place of y, you'd get 3 into 0, that gives you 0. Divide by 2 is again a 0. 3 minus 0 is 3. So we got the next point. And the last, let us take a 4 in place of y. The 4 gets divided by 2 gives you a 2. 3 2s gives you 6. 3 minus 6 gives you a minus 3. If I look at the pair of points which we have obtained, or the coordinates of the points, it's 0, 2, 3, 0, minus 3, 4. So we have obtained 3 coordinates or 3 points which lie on the line 2x plus 3y minus 6 equals to 0. Let us look at one more equation in this system. The next equation that we would take here is 4x plus 6y minus 24 equals to 0. Reduce to, this gives me 4x equals to 24 minus 6y. Dividing each and every term by 4, I would get x is equal to 6 minus 6y upon 4, which can be reduced to 6 minus 3y upon 2. Again here we have a denominator 2. To take care of this denominator 2, we would try to take different values for y. And the values for y definitely should be even numbers to avoid decimal numbers. Let us start with 3 set of values x, y, x, y. We begin again over here with y equal to 0. When I put y equal to 0, the term after the minus sign vanishes. We get x is equal to 6. Let us put the next even number, say 2. 2 gets cancelled with 2. 6 minus 3 gives us 3. Let us put the next even number, say 4. When I substitute 4 here, I would get 2 dividing by 4, giving you 2. 3 2s gives you 6. 6 minus 6 gives us a 0. So this is 6, 0, 3, 2 and 0, 4 are the 3 points which lie on this line. Let us see what the graph of these two lines looks like. The graph which we have plotted comes out to be 2 parallel lines, as you can observe here. Now these 2 parallel lines by their definition will never intersect each other. If they do not intersect each other, can they ever have any common point? No, they will not have any common point, meaning this system of equation will not have a solution. If this system of equation doesn't have a solution, such a system of equations is known as inconsistent system, meaning it does not have any common solution for both the equation, or there is no set of numbers which satisfies both the equations at the same point of time. So let us just have a quick review as to what did we learn today. We saw that if we take any pair of lines or any 2 equations which are linear together, there are 2 possibilities which can happen. The first is this system of equations can be consistent. That is, this system of equations can have common roots. Now the common roots can be of 2 types, that is unique, or they can be infinitely many. We also observed for unique roots that the coefficient of x of the first equation, that is a1, divided by the coefficient of x in the second equation, that is a2, is not equal to b1 upon b2, that is the corresponding coefficients of y in the first and the second equation. For infinitely many solutions, we observed that a1 upon a2 was equal to b1 upon b2 was equal to c1 upon c2. Both these conditions together give us common roots. Maybe they can be 1 or they can be infinitely many. In the case we have common roots, we call such a system of equations to be consistent. So when do we call them as inconsistent? A system of equations is called inconsistent when they do not have any common root. This was possible when the lines were parallel. That is, if we compare the ratios, we got a1 upon a2 was equal to b1 upon b2 but was not equal to c1 upon c2. Hope you understood that what are lines which are, or what is a system of equations which is consistent and which is a system of equations which is inconsistent. If you want to learn more of these type of activities, please do log in to www.letstute.com. Thank you.
The complete course for Math Grade 10th SSC Maharashtra State Board is now available in Pendrive and SD card format. Our quick revision chart book is also available in English and Marathi language. Click on the link to buy now. You may also check the description below. Thank you.